Hello guys, welcome you again for the fifth lecture in series on solar energy fundamentals. In this lecture we will try to develop mathematical equation to calculate the time of sunrise and sunset at any place on the earth. Also try to know how to calculate the day length. The day length for any place is important for the point of knowing the actual sunshine hours at the location, because the sunshine hours help in identifying the magnitude of available solar radiation at the surface. We know the input parameters for solar devices is solar radiation, and their magnitude and duration decides the output from the given solar device. We observe that at the time of sunrise the sun seems to be rising from the horizon, and at that time its rays are parallel to the horizon plane. So if this is the case, as shown in the picture, this is the earth and this is the sun, which is below horizon, and in the morning the sun is not visible to the observer. If the observer is standing on the earth surface here, we can call that this the point where the observer is standing is the reference point. In the morning, when the sun rises in the east and attain the place above horizon, at this position of the sun the very first ray emerges like this, then this ray is parallel to the horizon plane. I mean, any observer on the reference point will feel that rays are parallel to the earth's surface. Or you recall the earlier lecture number 4, where we discussed and concluded that any horizontal surface on the earth's surface will receive the rays parallel to it. So under such condition, this is the normal to the surface, and hence the angle of incidence which is between the normal to the surface and the sun ray is 90 degree. You are suggested to keep this statement in mind because this will be the basis of our next discussion. To derive an equation for sunrise and sunset, we have to recall the equation for angle of incidence. As we already know that cos theta is the angle of incidence, where cos theta is equal to sin phi sin delta cos beta plus cos delta cos gamma cos omega sin beta plus cos phi cos delta cos beta cos omega minus sin delta cos gamma sin beta plus cos delta sin gamma sin omega and sin beta. In our discussion we have already assumed that the surface is horizontal, it is laying on the earth surface, and at the time of sunrise the sun rays are parallel to it. So we can modify this equation of angle of incidence, because in this equation the angle beta is representing the inclination of the surface. So if we assume that the surface is not inclined, it is horizontal, then beta is equal to 0, and we have to place the value of beta in the equation of angle of incidence. So when we place the value of cos beta here, then in this term the cos beta will be cos 0, and in this term also the sin beta will be sin 0. So wherever we having a cos beta, that cos beta will be replaced by cos 0 and sin beta will be replaced by sin 0. So after putting the value of beta in the terms, in the trigonometry we know that the value of cos 0 is nothing but it is cos 0 is 1 and sin 0 is 0. So if we place the value of cos 0 and sin 0 in the terms, then in that case this term cos delta cos gamma cos omega will be 0, and also the term sin delta cos omega and sin 0 will be 0, and this term will also be 0. So after considering these, the final equation for angle of incidence for a horizontal surface will be cos theta sin phi sin delta plus cos phi cos delta cos omega. Now we have to produce further to derive an equation for sunrise, sunset and day length. Reproduce the equation of angle of incidence for horizontal surface, as we are already aware of it. In the discussion previously we have concluded that the rays are parallel to the horizontal surface, and hence the angle of incidence at the time of sunrise is 90 degree. So if we place the value of theta, if the theta is 90 degree and we place the value of it, the equation will be cos 90 equal to sin phi sin delta cos phi cos delta and cos omega. We know that the value of cos 90 is nothing but it is 0. So we will place the value of cos 90 here. The equation will be 0 equal to sin phi sin delta cos phi cos delta cos omega. Now we have to rearrange this equation, and this term, the cos phi cos delta cos omega, will take another side of the sign of equality, means on the left side of it, and we can rewrite it like that: cos phi cos delta cos omega is equal to minus sin phi sin delta. Here omega is the R angle. This omega defines the timing of sunrise and sunset. Then further we have to write it that in place of omega we have to write omega s. The omega s actually define that it is no more an R angle. Actually this is the angle for sunrise to solar noon, half part of it. So further if we resolve this equation, then we having a cos omega s, and we take this term cos phi cos delta other side of it, then we having a sin phi sin delta divided by cos phi cos delta. And from the trigonometry we know that these two terms, means this sin phi by cos phi is what it is, tan phi, and to sin delta cos delta we can write that this is the tan delta. And if we'll take the cos on the other side of the sign of equality, then we having a equation omega s is equal to cos inverse minus tan phi tan delta. So this is the equation which gives the R angle from sunrise to the solar noon, and this angle is depending on the place where the surface is located and the position of the sun on that particular day. Means the declination and the latitude are the two important angles which are required for finding out the day length of any place on any day of the year. Now we will see here the concept of the sunrise, sunset and day length. The R angle corresponding to sunrise and sunset on a horizontal surface can be calculated by using the equation omega s is equal to cos inverse minus within bracket tan phi tan delta. We all know that phi represents the latitude of the place and delta is the declination, tells the position of the sun. Further, the corresponding day length in hours can be calculated by using the equation smx. Smx is equal to 2 by 15 omega s. Now how to calculate the day length in hours, minutes and seconds by using this equation, that we will see by taking some example in the end. But at this time we need to know that why in this day length equation this omega s is multiplied by 2 and it is divided by 15. What is the significance of it? That we will try to understand. To understand it, let us recall that while deriving the equation of omega s is equal to cos inverse minus tan phi tan delta, we have considered the value of theta is equal to 90 degree. It means we had assumed that the sun rises in the morning at horizon is parallel to any reference point on the earth surface. Now question arises why we have taken theta as 90 degree. To understand this, let us consider a horizontal surface. This one is the horizontal surface and a normal to the surface. In the morning at the time of sunrise, the position of the sun is parallel to horizon. This is the horizon and the position of the sun is parallel to it. And as the day goes, the sun rises and at solar noon it attains the vertical position like this. So this is the vertical position at the normal. The sun is at the top during the solar noon, just right above this normal. But this movement of the sun from this point to the solar noon is the movement which is considered during the first half of the day. Means that is why the angle subtended between this normal and this horizontal line is 90 degree. It means the sun continue to displace its position from solar noon till it sunsets. So how it goes? It goes like this. It means from there it also continue to move and it goes below horizon, and this is the sunset point where from this reference point the sun is now not visible to the observer. So now it is clear that this equation omega s represents the only one half of the sun path traversed in an R angle, and for representing the path traversed in a whole day from sun rising till sunset, the value of omega s needs to be twice. Hence this equation is multiplied by 2. Also we know that the value of 15 degree of omega s is equivalent to 1 hour. I mean the rotation of earth takes 1 hour for every 15 degree of rotation. So when we will put the value of phi and delta in this equation, we will get the two values of omega. One value is positive and another is negative. The positive value corresponding to the sunrise means the first half of the day, and negative corresponds to the sunset, that is another half of the day. But together these values represents the complete path traversed by the sun. Till now we learned that how to calculate the day length if the surface is horizontal. Now let us see what would happen if surface is inclined and facing due south. I mean that what will be the equation for day length in such a situation? How this equation will be different than that of horizontal surface. So first let us rewrite the general equation for angle of incidence cos theta, a very familiar equation. We are very much familiar with this equation, that angle of incidence cos theta is equal to sin phi within bracket sin delta cos beta plus cos delta cos omega cos gamma sin beta bracket close plus cos phi is equal to within bracket cos delta cos beta cos omega minus sin delta cos omega sin beta bracket close plus cos delta sin gamma sin omega sin beta. Now for surface facing due south, the value of azimuth angle gamma is equal to 0 because it is facing due south. If we'll place this value of gamma equal to 0 in the above equation of cos theta, then we will having a new equation, and in this equation cos gamma is replaced by cos 0, and similarly in the another equation where the cos gamma is replaced by cos 0, and this is the last equation where last term of the equation where sin gamma is replaced by sin 0. And from trigonometry we know that the value of cos 0 means this term, and this term is 1. Okay, so this is 1 and this is 1, but in this case the value of sin 0 is 0. So by considering the value of cos 0 and sin 0, if we rewrite this equation, then in such a condition the term of cos 0 will be replaced by unity, and the term of the sin 0 becomes 0, because whole term if it is multiplied by 0 becomes 0. So the new equation will be this: cos theta is nothing but sin phi sin delta cos beta, and here it is cos delta cos omega and sin beta, plus next term is plus cos phi within bracket cos delta cos beta cos omega minus sin delta sin beta, and this equation will be 0. Now we have to solve this equation and multiply this sin phi with the bracketed term, and cos phi is also with the bracketed term, and the new equation will emerge like this. Here within the bracket the sin phi sin delta cos beta plus cos delta cos omega sin phi sin beta bracket close, plus within bracket cos phi cos delta cos beta cos omega minus cos phi sin delta sin beta. Now we'll further solve this equation, and these two terms will take on one side, and this term and this term will take on another side, and the equation will be like this. Now this cos delta cos omega sin phi and sin beta plus this cos phi cos delta cos beta cos omega, the bracket close, plus then we have to take this sin delta sin phi cos beta minus sin delta cos phi sin beta. So we having these two terms, one is this and another one is this, these two bracketed terms we have. Now we have to further resolve these equations, and in the first bracketed term we will find that the cos delta cos omega means these terms, cos delta this one and cos omega this one, these are the common term, then we have to take them outside the bracket, and similarly in this only the sin delta is the common term, we have to take outside the bracket, and the new equation will be cos theta is equal to cos delta cos omega within bracket sin phi sin beta plus cos beta cos phi, plus sin delta is outside the bracket, and within the bracket will be sin phi cos beta cos phi sin beta. From trigonometry point of view, we'll see that this is sin A sin B and this is cos A cos B, and here this is a sin A cos B and this is cos A cos B. So how we can write it? Further we resolve it. So this term cos delta cos omega is outside, and within bracket this sin A sin B plus cos A cos B become cos phi minus beta, and this term will be sin phi minus beta. Now this equation of inclined surface which is facing due south is reduced to this equation. So this equation of angle of incidence for the inclined surface facing due south is reproduced here. Now we are interested in to find out the R angle and the situation of sunrise and sunset timing when the surface is inclined. So to derive this equation, we have to follow the similar line which we did in the horizontal surface. In this case also, take the theta is equal to 90 degree. Means here also we have to take, assume that during the sunrise or sunset, the sun is below the horizon and with the normal to the surface makes an angle 90 degree. So if you place the value of 90 degree, this theta value here, so the cos 90 is 0. So we are reproducing this equation here, the cos 90 is 0 and rest of the equation will go like this. We are reproducing this equation like this. Now we have to rearrange this equation and take this term on the left side of the sign of equality and keep this term on the right side of the sign of equality, and the equation will go like this. Cos delta cos omega cos phi minus beta is equal to sin delta sin phi minus beta. Since this equation was taken on the another side of the sign of equality, that's why this minus sign is placed for this equation. Now the term omega in cos omega we have to write as omega s, and now cos omega becomes the cos omega s. Now taking this cos delta and cos phi minus beta on the right side of the sign of equality, and the equation will becomes cos omega s is equal to sin delta sin phi minus beta divided by this cos delta and cos phi minus beta. Now we know that sin phi minus beta over cos phi minus beta is tan phi minus beta, and sin delta over cos delta is tan delta. So this equation will now reduce to minus tan phi minus beta and tan delta. So this is the equation for R angle we have to calculate if the surface is inclined and facing due south. But in this case the two situation arises. The situation 1 is where sun is in the southern hemisphere, but I would like to make it clear to the audience that all the above equation for the R angle has been derived considering that the surface is in the northern hemisphere. So when the surface is lying in the northern hemisphere but sun is in the southern hemisphere, it is the period of between September 22 to March 21. So in that case R angle omega s can be calculated by using the equation cos inverse minus tan phi tan delta, and this equation is similar to that of horizontal surface what we have derived earlier. Situation 2 will be surface is in the northern hemisphere and sun is also in the northern hemisphere. So the situation or the time period of the northern hemisphere will be between the March 22 to the September 22. So in that case the value of the omega s can be calculated by using the equation cos inverse minus tan phi minus beta tan delta, means this equation. It means we having a two different equation for the two different duration of the year. This makes difficult for the students or for the designers to take care of the situation. Now how to deal with this situation we have to see. As we were discussing, now we have two equations for two different situations. First one is when sun is in the southern hemisphere, and second one is when it is in the northern hemisphere, and these two different equations goes like this. Then how to calculate it? For these two equations we have to follow this equation that omega s minimum of within mode of cos inverse minus tan phi tan delta or mode of cos inverse tan phi minus beta tan delta. So if we'll calculate the value of omega s by using these two different equations, the minimum value which we are getting out of this will be considered as the R angle for the whole day. Audience may take care of the sign convention because delta is negative for situation 1. Here when the sun is in the northern hemisphere, the delta is negative, and for this situation the delta is considered to be positive. Now let us learn something more. Till now we have learned that the surface is inclined. It is in the northern hemisphere and it is facing due south. But the situation is surface is inclined in the northern hemisphere itself, but it is facing due north. Then how to proceed? We have to proceed in the same manner, but in this case the gamma we have to take 0, and by placing the value of gamma equal to 0 in the equation of angle of incidence, we have to derive the equation, and we'll get the value of R angle omega s equal to cos inverse tan phi plus beta tan delta. So what we have seen, when the surface is facing due south in the northern hemisphere and it is inclined, then here is a sign, negative sign, that is phi minus beta we are taking, but if it is facing due south, then we are taking the phi plus beta. So this is the difference between the two situations. And in this situation also, when the sun is in the southern hemisphere, in that case we have to use this equation for calculating the value of R angle, just similar to the horizontal surface. And when the sun is in the northern hemisphere itself, then we have to use this equation for calculating the value of the omega s. And hence we have to calculate both these values, and we are getting the different value for the R angle, then we have to take the minimum of it. Means whatever the less value either we are getting from this equation or we are getting from this equation, we have to consider the minimum value for that. Till now we learned how to calculate the R angle theoretically. Now we'll take a numerical problem on it and we'll see how to calculate the R angle for different days of the year. The problem is calculate the R angle at sunrise and sunset on June 21, September 21, December 21 and March 21 for a surface inclined at an angle of 30 degree and the surface is facing due south. Means in this particular case the gamma is 0 and beta is 30 degree. The surface is located in Delhi and the coordinates of the Delhis are given. So latitude is 28.704 degree north and longitude is 77.1025 degree east. Determine the R angle on the corresponding day at Delhi. It means at Delhi, at this location, we have to calculate the R angle for June 21, September 21, December 21 and March 21. Now how to solve it? First we have to display the dates, the June 21, September 21, December 21 and March 22. These are the particular dates for which we have to calculate the R angle. And for calculating the R angle, we require the two important angle, that is latitude where the surface is placed and the sun's apparent position on that particular day, means the delta. So for calculating the delta, the requirement is we have to find out the Julian day of the year. Say in case of the June 21, the N is 172. We will start counting from 1st January till June 21. The N values come out to be 172. And for calculating the declination angle, we have to use this equation, and in this equation the value of N we have to calculate just simply counting from January 1 till the date is there, and delta is coming out to be 23.45 degree. If we take the case of September 21, the value of N is 264, and by placing into the equation we will get the delta is minus 0.2 degree. For December 21, the value of N is 355 degree and delta is minus 23.45 degree, and March 22 the N is 81 and delta is 0. So what we can conclude from these values is on June 21 the angle of declination is 23.45 degree. It means the sun apparent position is on the Tropic of Cancer. It is located in northern hemisphere. On December 21, the value of delta is minus 23.45 degree. It means it is located in southern hemisphere at Tropic of Capricorn. Where on September 21, the value of del is almost 0, and on March 22 it is 0. So it means on September 21 and March 22, means sun is located on equator. Now we have to take the case wise. So the case 1 is June 21, and for that the another angle which is required is the phi, which already been told that the surface is located in Delhi and its angle of latitude is 28.7 704.741 degree. Now to calculate the R angle, we need to use this equation omega s, that is minimum of cos inverse tan phi tan delta or cos inverse tan phi minus beta delta. So we have to place the value of phi, delta and beta in this equation, and what we can get out of it, the phi is 28.704 degree and delta is 23.45 on June 21, and this is phi minus beta, and this is again a delta, that is 23.45. So if we further resolve it, so what we are going to have, the value of these angles of tangent of delta and phi minus beta we are having here, and when we multiply these numerical values, so in this case the minus becomes the plus, and cos inverse is also the plus value we are getting, and here we have a cos inverse minus value we are having, and when we resolve it, so what we are going to have, the minimum of 103.7 degree and 89.45 degree. It shows that if the surface is horizontal, then the R angle will be on June 21 will be 103.7 degree, but if surface is inclined, then it becomes 89.45 degree. But as per the instruction, we have to take the minimum value of it. So on June 21, the value of R angle for the calculation point of view, we have to take 89.45 degree. Similarly, we'll take the case 2. In case 2, it's a day of September 21, and phi and delta we have already been calculated. The value of delta and phi is already known to us for the location, and this is again the equation is repeated just for the sake of recalling it. And if we place the value of phi delta accordingly, then what we are going to have from it is this. So here the phi minus beta will give the tangent of minus 1.296, and this brings a significant change in the values, and here we are going to have the minus 0.022, and the outcome of that will be, we are getting the two angles 89.9 degree and 90 degree. So almost on September 21, means when the sun's apparent position is at equator, then either the surface is horizontal or it is inclined, doesn't make any difference, and the sunshine hours or R angle will be the same almost. If we take the next case, that is for the December 21, on that particular day the sun is on the Tropic of Capricorn, because delta is minus 23.45 degree, and if you place the values, means you have to see this equation. In this equation, the phi delta and phi minus beta, if we are placing over here and we resolve it further, so we are going to have these values, because phi minus beta is there, only the difference is now, in this case the delta was minus 0.2 degree, but here delta is minus 23.45 degree, and because of that what we are going to have, the value of omega r, if the surface is horizontally placed on the location, is 76.26 degree and 90.54 degree if it is inclined by 30 degree. And if we'll say take the case 4, that is on March, so this is not a 3 but it's a case 4. So if you're taking a case 4, sun is at equator because the declination is 0, and again we have to use the same equation. We place the value of phi and delta in that. So in that case, since tan 0 is 0 in both the cases, so what we are going to have, cos inverse 0 and cos inverse 0. So exactly the values we are getting is the 90 degree in both the cases. It means again it is proved, whether it is a September 21 or the March 22, if the sun is on the equator, so in both the cases the R angle will be similar irrespective of the inclination of the surface. In order to summarize it, they are placed in a tabular form for all the 4 days for which the R angle is calculated. And here what is we are able to observe, what we have observed from this table, this is very important. If we see the value of R angle for horizontal surface when beta is 0 and surface has given inclination when beta is equal to 30 degree. So in case of the horizontal surface when beta is 0 degree, what we are going to observe, that we have a values of minimum 76.26 degree on December 21, means when the sun is at Tropic of Capricorn, and 103.7 degree when sun is at the Tropic of Cancer. So in case of the horizontal surface, R angle varies between the minimum of 76.26 degree on December 21 to the maximum of 103.7 degree on June 21. This variation is of around 36 degree. It means during whole day on June 21, the horizontal surface receives sun radiation for 3 hours and 40 minutes more than that of the same surface at the same location received on December 21. Whereas if the surface is inclined, means beta is 30 degree, then irrespective of the day of the year, the duration of the sun radiation received by the surface is almost same, because we will see the values of it. All are almost 90 degree. There is a very little variation of 0.5 degree. So this has a great significance, and out of this outcome I am going to make a very important statement. The sun appears to move back and forth between the Tropic of Cancer and Tropics of Capricorn throughout the year. Therefore, whether a solar device is located inside or outside the tropical belt, the duration of sun's radiation falling on the surface varies. As a result, the output or performance of the device also varies to the same extent. This makes the device technically unviable or significantly degrades performance for a certain time of year at a specific location.